The third step in the linearization of the boundary conditions is the balance of pressure or the balance of normal forces for different points on the interface. Because the flow is irrotational, I can use the Bernoulli's equation for different points in the flow field. This is the Bernoulli's equation. This is the constant of the Bernoulli's equation. And this term is the unsteady term. And this one is the gradient of phi is equal to the velocity vector. So this is the square of the velocity. And the last term is the gravity force in the Bernoulli's equation. For the pressure of 2 points located on the interface is equal because I've ignored the surface tension. If you want to add the surface tension into your analysis, it should be added to the balance of pressure because the surface tension changes the balance of pressure of 2 points on the interface. So, but here, because the surface tension has been ignored, the pressure of point 1 and the pressure of point 2, both located on the interface, are identical. So this is the Bernoulli's equation, which is written for point 1, and this is the pressure of point 1 based on the Bernoulli's equation, which is equal to the pressure of point 2. Points 1 and 2 both are located on the interface, and the interface is shown by the eta function. So replace z by eta here because these are the pressures of the point on the interface or on the eta function. And also we have the partial derivative of phi 1, for example, with respect to time. As you see here, take the derivative of both sides with respect to time. The derivative of this term with respect to time is 0 because x and t are independent variables in Eulerian frame. So the time derivative of phi 1 is equal to the time derivative of phi hat 1. So this is the phi 1 and this is the phi hat 1 with respect to time. And again, the phi hat 2 with respect to t. These are linear operators. But here we have again a nonlinear term. This is the gradient of phi I, for example, phi 1. Take the gradient of phi 1. So we have the gradient of the second side of the equation. So copy and paste this term here. This is the gradient of u1x plus the gradient of phi hat 1. Again, this is the gradient of u2x plus gradient of phi hat 2. As you see, these terms are nonlinear and they should be linearized. Simplify this equation for the case with no disturbance. When there is no disturbance in the equation, so the eta is equal to 0. Because the interface is located at 0 equal to z equal to 0. So these terms engaged with eta vanish. And because the disturbances are 0, so phi hat 1 and phi hat 2 are both again 0. So C1 minus this term remains on the first hand side. So the gradient of u1x is u1 and 2 other components are 0. So u1 to the power of 2 and c2 minus rho 2 over 2 u2 to the power of 2. This is the simplified form of the dynamic condition or the balance of pressure for the case with no disturbance, which helps us to linearize the dynamic condition. Alright, let's continue the linearization of the balance of pressure or the dynamic linearization. We have a nonlinear term here. So I want to expand this term. You see gradient of u1x plus the gradient of the disturbance phi hat 1 to the power of 2. Gradient of u1x is a vector u1, 0, 0. And gradient of phi 1 is gradient of phi hat 1 x, y, z. So this is a this is a positive line. So the first component of the sum of these vectors is u1 plus partial derivative of phi hat 1 with respect to x, and the other components are as follows. This is not the power of 2. This is the dot product of this vector with itself. So perform the dot product. This is the result of the dot product of this vector with itself. These are second order terms or the nonlinear terms because the unknown, which is the disturbance of phi function, is multiplied to itself, or we have a power of 2 here. Expand this term, again another second order term appears here during the expansion of this term. So we have only this zero order term, and this is the first order term. Ignore 3 other second order terms. This is the linearization of this dynamic condition. So just keep these terms and replace them in the balance of pressure using the Bernoulli's equation. So copy and paste the balance of pressure here, but this is the constant of Bernoulli's equation C1. This is the time term, and we have 2 new terms here because I replaced the nonlinear term with the linearized version, and the last term is again identical to the last term here. This is P1, and the second side of the equality is the P2. Here, based on the simplified form of the Bernoulli's equation for the case with no disturbance, you can cancel the 4 terms from both sides of the equation. As you see, again, these 4 terms are completely similar to the balance of pressure for undisturbed case. So this is the final form of the balance of pressure, or the dynamic pressure, or the linearized dynamic condition, which is true for z equal to 0. This is again the kinematic linearization, and this is the dynamic linearization. So we have 4 equations on the board. Equations 1 and 2 are the linearized version of the adhesion kinematic condition. Equation 4 again is the kinematic linearization of the interface, which is true when the disturbance is small. And equation 3 is the linearized version of the balance of pressure, or the dynamic linearization of the pressure boundary condition, or continuous pressure variation across the interface.